Good evening, everybody. Today I'm going to give a talk about cryptographic operations in the browser. First, I will talk a bit about who am I. So I'm Nick van den Bleeken. I work for Inventive Designers. More importantly for this talk today, I'm also a member of the W3C working group, the Web Cryptography working group. You can find me on Twitter, and there will be a demo on later on, and that demo, the source of that demo is available at GitHub. So what I will be talking about today is why we need cryptography on the web, why we need a Web Cryptography API, what you can do with it using. I will present some real-life use cases, then who's implementing it, then I will follow with a demo, and then what is next. So why do we need cryptography on the web? So using it, we can easily and securely authenticate people. You can sign and verify messages and documents, or you can encrypt or decrypt messages. Later on, I will give some more use cases to elaborate on this. It's not about SSL or TLS, but really cryptographic operations on the web. So, because JavaScript is the language of the web, you might think of, oh, I could just Google and search for a cryptographic library in JavaScript. There are lots of them. Here are some examples. For example, the Stanford JavaScript crypto library, Crypto.js by Google, GSBN, OpenPGP, and some of the frameworks already also have a crypto modules like Closure and DojoX. But there is a problem with those JavaScript implementations. They are implemented completely in JavaScript, and in JavaScript it's really hard to protect against timing attacks. So in all the cryptographic operations, it's important that you can ensure that certain operations are done in a constant time, because otherwise there are attacks to get your input from it. And in the browser, because the browser vendors are always optimizing the JavaScript engine, those timings change over time, and also the optimizations are really different between different kind of browsers. So it's really hard to get a constant time in JavaScript. Also, the mod.random is not a secure random generator, and for seeding your algorithms, you need secure random numbers. It's also really hard to get the implementation correct, because all those algorithms are really complex, and you need quite good cryptographers to implement them without any flaws. And it's really hard to find good cryptographers that are also skilled JavaScript developers. And then the last problem is performance, because in JavaScript you don't have access to hardware acceleration for doing the encryption, and also all numbers are 64-bit floats, and yeah, in cryptography you need a lot of big-ins. So we're at a Java conference, so you might think, oh, the solution is just using a Java plugin, an applet, to do the cryptographic operations and call it from JavaScript. But with that, there are a couple of problems. So lately, there have been a lot of Java security vulnerabilities found in Java, sadly. And some browser vendors decided to disable the Java runtime by default, and you have to enable it, so it's really hard, or people have to enable it. Also, in the US, the Department of Homeland Security recommended in turning off Java in your browsers, and because there are coming a lot, or almost everybody now has a mobile device, and on mobile devices you're not able to run a Java applet in a web browser, so that's also not an option. Another option you can think of is just creating your own native extension to implement all the crypto operations, but it has more or less the same disadvantages. You have to install it separately. It's browser specific. Some browsers are about to drop support for native extensions, and it's also not available on mobile. So that's why W3C has decided that there needs to be a native implementation in the browser that provides a JavaScript API to do the crypto operations. So the work started some time ago, and all major browser vendors, Google, Mozilla, Microsoft, and Apple, joined the working group together with a lot of other companies, Netflix, Inventive Designers, the company that I work with, but also companies from all around the world. And our goal is to provide a cryptographic implementation in the browsers, which is implemented natively, and that can be called from JavaScript. It will be available on desktop browsers, but also on mobile, on televisions, and all other devices that will have a browser will probably get it. So now we will go through some use cases with what you can do with such an API. So the first use case is about banking transactions. So suppose that John opens a bank account and he wants to authenticate with the bank, sign some documents and transactions, so that the bank knows that they are from him, and he wants to send some documents to the bank that only the bank can read, and he wants to receive documents that only he can read and nobody else. So the first thing to get started is that he needs to generate keys to do all those operations. So but the bank has to be sure that the keys that are generated are from John. So John has to get a one-time verification code with which he can identify himself. So he can get it by SMS, and a token generator that most of the banks already have of another device, or maybe just a plain letter that they get by post. So then the bank asks if John isn't using a browser in a public place, a kiosk or something like that, because if it's on a kiosk, you don't want to get your private keys on that machine. When John said that he's not on a public computer, he can generate his key pair, its public and private key. And then with that key pair, he can sign his documents to authenticate himself. And then he stores, and of course, you want to store the key pair locally in the client, so he doesn't have to go through the process of identifying him. When it's stored on the browser, you also want to provide your public key to the bank, so that the bank can verify that it's actually you that is signing a document. And you want to accept the public key from the bank, because when the bank signs something, you want to verify that it's actually the bank that is doing it. So now I will go through some code samples about how you will do it with the JavaScript API. So first, you have to create a dictionary that identifies the algorithm that you will be using for the encryption operation. So here we've chosen a signing algorithm. Here it's RSA, SSA, PKCS1. And for that algorithm, you have to provide some parameters to generate a key from it. So in this case, for the RSA, it's a modulus length and a public exponent that you have to specify. If you have that object, you can create the key by calling the generate key function, providing it the algorithm and 2 extra parameters. The first one is a Boolean that indicates that if you want to be able to extract the private key from the key store. In this case, we don't have to extract it, so we specify false. And you also have to specify which operations you want to do with the key. because generating a key takes some time, we want to do it asynchronously and don't block the UI thread. So that's why you provide a callback function. When the algorithm is generated, it will be when the key is generated, it would get called, and you can store your key pair using IndexedDB or local storage, and you can send your public key to the bank. So now we have the key pair to identify ourselves. Yeah, and you can also provide, of course, an error when callback for something if something goes wrong. In this case, it just logs it to the console. In a real life application, of course, you will do something sensible with it. So now the next part is step is that you have to get the public key from the bank, and the bank can provide the key however it wants it, but a good serialization of a key could be in a JSON web key format, and that JSON web key will be embedded in a JSON web token. If you get that key from the key data from the bank, you can parse the JSON object, and then you have the information of your public key. If you have that, you can provide it on the import key to the import key function and import the key. You also have to specify which algorithm to use. If the key should be extractable, and what operations you want to do on the key. If it is imported, you can store it again in local storage for further use. So now that we have generated our key pair, we can use it to authenticate it, authenticate ourselves when in the future when we want to access the bank site, the website of the bank. All your communication that you're doing with the bank still has to go over TLS, because you don't. This key pair is just protecting you for authenticating yourself, but you don't want the communication to be sniffable. So how can we authenticate ourselves then using the key pair? So the bank could send us a message that is encrypted with our public key, so only we can decrypt it, and it can sign that message using his public key, so that we can know for sure that the bank was sending us that message. So the next step will be that we receive the message, that we verify the signature of the bank, and decipher the message with our private key. Then the next step is that we sign the document, the message, with our private key, send it back to the bank, and now the bank can check if it's actually John that is trying to connect to the bank. So how do you do that in using the Web Crypto API? First, of course, you get the public key of the bank. In this example, it's again in a JSON web token. We extract the signature and the message from the data, and then we also have to get the public key out of our local storage from the bank. And then the bank will sign the document, and we have to verify it. So we create again a dictionary specifying the algorithm that we use to sign the message, and a parameter which hash is used to hash the data that is signed. So if we have all that information, we can just call the verify, and then specifying the dictionary that contains the algorithm, the public key of the bank, and the data, the signature that we got from the bank. If that signature, if the signature is valid, it will call our callback, and then we can decrypt the message again using the our private key, providing it the message and specifying which algorithm to use. If we don't, if it's not valid, the signature, we know that that it's not the bank that is trying, that is sending us the message, but somebody else, and then so we just stop, and we know that we're not talking with the bank's website, but with somebody else. If we decrypted the message, then we can sign the message with our private key, so the bank afterwards can be sure that it's John trying to make a connection with the bank. Again, we retrieve our private key. We use the sign operation. We specify the dictionary saying specifying the algorithm to use to sign, and the hash function, provide our private key, and what we sign is the decrypted message. If that succeeds, then we can send back the signed message, and the bank can verify that it's actually John that's trying to connect and not somebody else. So now that we, as long as the keys are valid, we can use the generated keys to sign documents, verify signatures, encrypt documents, and decrypt documents. What are other things that we can do with documents is we can use the sign function to authorize payments, to sign forms or sign other documents. But what we can also do is we can submit documents that only the bank can read. So and the bank can be sure that we submitted the document. So how can we do that? So we use a sign operation to sign the document. Then we generate a symmetrical key. You want to use a symmetrical key because an asymmetrical key can only encrypt the number of, or a bit less than the number of bits of his key, and a document can of course be bigger of that. So we generate a symmetric key, we encrypt it using the symmetric key, and we wrap the message using our asymmetric key, so our private key, and now the bank can decrypt it with our public key, and nobody else can decrypt it because they require our public key to read the document. A bit in the same lines is we can receive encrypted documents from the bank that only we can read. So first, we verify that the document is from the bank by using the verify operation. We unwrap the asymmetric, using asymmetrical unwrap to get the symmetric key that the bank used to encrypt the document, and then we can read the document. So what are other use cases? For example, you want to store documents in the cloud and you won't be able, or want to be sure that nobody else can read those documents. So you want to store them encrypted on the web, but you don't want to do the encryption on the server, but you want to do it in the web browser, because otherwise you're sending your documents in plain text or readable over the internet to the server, and they can read your document. So here you want to store the encrypted document and retrieve the encrypted document and decrypt it. And of course, you first want to make sure that only you can get the encrypted documents, and for that you use authentication. So for the authentication, we can use the same strategy that we did with the banking use case. For storing encrypted documents, we are going to use a key to encrypt them, of course, but here we're not going to generate a key from a random number, but we want to derive the key from a passphrase, because if you're using another computer, you want to also be able to retrieve your documents and decrypt them. So there we use an HMAC SHA-1, and we derive a symmetrical key from from our password. I will go into details in the next slide. We use the same way to decrypt the document because it's a symmetrical key. So it's the same key that we use to decrypt. So how would you do that? So first you have to get some parameters. So you need a salt because you don't want if two users have the same password that they will result in the same hash, so that you want to make sure that it's not guessable, or you want to make it more difficult to guess the password. You also want to specify a number of iterations, because to make it harder to decrypt it, you want to run the algorithm a couple of times to make it more compute intensive to try to, if somebody wants to hack your key to get your decrypted document. And then, of course, because we're going to derive the key, you have to specify the algorithm that you want to use. In this case, we are going to use a password-based. The password-based key derivation function too. We provided the salt, the iterations, the password or the passphrase, and then for this, you also have to provide a pseudo-random function. And in this case, we're using HMAC with a SHA-1. It's a particular RFC in which it is specified that this is a secure way to do that. So instead of generating the key, we derive the key specifying the algorithm, which we defined above. Then we specify what type of key we want to generate. In this example, we want to use a symmetrical key. So here I choose AES GCM. And we have to specify the key length. And of course, if it's extractable and what operation that we want to do with the key. If the derived key has finished, we can use the key to decrypt or encrypt our documents. Another use case is off-the-record real-time messaging. So, for example, John and Joe want to communicate with each other, but they want to make sure that nobody can read their messages. So it can be text or even data, photos, videos. So they want to use encryption. So how does this work? They generate asymmetric keys for each other using the same thing that we've done before. Then they use a Diffie-Hellman algorithm to exchange their keys. And then they can encrypt or start communicating with each other, ensuring that that they send the message and that only the other party can decrypt or read the message. Another use case is code sanctity and bandwidth saver. So here the use case is that you don't want to go to your CDN to get your JavaScript served, but that you want to store it locally to prevent round trips to your CDN. And we also want to support library upgrades and want to make sure that the JavaScript that we run is actually the JavaScript that we served and nobody has tampered with it in the local storage. So how could we do that? We could get a hash from our server that says this is the hash of the JavaScript file. Then we can use a digest function, or we retrieve the JavaScript from our local storage and we use a digest to calculate the hash. If the hash is correct, is the same, we know it's the same version of the JavaScript, so we can safely run that JavaScript, and we don't. If it's not the same hash, then we just fetch it from our CDN. So, after all those examples, you might be thinking, whoa, this is a bit low level, where is the higher level API? I'm not a crypto, because I'm not a crypto guy, and there are quite some things that I can do wrong. So So you might be thinking or wanting a high-level API. So at the W3C working group, we first thought, oh, we're going to define first our low-level API, then we will build a high-level API on top of it, but it was really hard to define one high-level API because, as you've seen, there are so many different use cases. Coming up with one high-level API where everybody can agree on is really hard. There are some examples, for example, SALT, Caesar, and SGCL are doing that, but then it's, some people prefer SALT, some people prefer Caesar, so it was really hard to choose one. And then a lot of people, there was some discussions, and then we came to a conclusion that almost everybody that is creating a website is already using frameworks like jQuery, Dojo, YUI, Prototype, or other things. So all those libraries can provide a high-level API using our low-level API, because there it's no longer a problem with the with performance or the constant time, because the low-level API is done natively, but you can write a JavaScript API, make it high-level JavaScript API, making it easier for the web developer. So that's why we decided that we will, for now, not create a high-level API. So just to recap a bit, so why does it need to be implemented natively? To protect, the first thing is we want to protect against timing attacks. If it's implemented natively, we can more securely store the key material, so from your private key, the really important bits that you don't want to give to somebody else. We have access to a secure random generator. Browser vendors can hire really good cryptographers to implement it, and we can get better performance. So now the important part, if you want to use it, who is implementing it? So Microsoft in E11 already implements a version of the Web Crypto spec. Chromium implements it. You have to enable it with flags. Actually, it's already in the stable Chrome build now, but you still have to enable it with flags, so that you can't use in the wild yet, because it's not likely that people have enabled it. In Mozilla, it's still they are under development, and it's not yet, they didn't have anything published yet. And for now, to get used to the API and to play with it, you could use a JavaScript polyfill that implements it completely in JavaScript, which of course you don't want to use in production because of all the reasons why we need a native implementation, but it's a good starting point to now already experiment with it and give feedback saying, oh, I can't do that use case with it, or maybe we should change the API a bit more because that's a problem with it. So that's why there is a really good polyfill implemented. There is also another specification that we are working on in the working group, and that's the Web Crypto Key Discovery. It's to discover keys that are pre-provisioned out of band. We don't specify how it's pre-provisioned, but for example, Netflix is using this on their on certain TVs are pre-provisioning keys with a specific name, and then they can use that key in their application. So now it's time for a demo. I will be demonstrating the operations in a couple of browsers. I will first start with Chromium. All the source code of this demo is available on GitHub. You can have a look at it if you're interested. So the first example is creating a digest. So here in the log you can see that it is using the Web Crypto API, because I enabled the flag, so it's available in this browser. So here, for example, this devox. So here you can see that it calculates the hash. Another, oh yeah, I will come back at this on a later state. The Chromium build doesn't support import and export of keys, so to do signing, you can't use it yet. The Chromium build, because you have to be able to export and import your key to give it to the other party and to import the key from the other party. So for that, I can use that in Safari here because there is no native Web Crypto API available in this browser. The example falls back to to Polycrypt, which is a polyfill that fully implements the API. So to get started, I first have to generate the keys. Here you see that it's done in JavaScript, and it takes quite some time to generate the key. I will copy my public key. I will go to Windows. So I have to log in. So here in the sign, I also generate the key. Here you see that it's much faster. I put in the key of the public key of the other party, and now I go back to the other browser. I sign a message. I copy the signature to the other browser. Here you see it is red. The signature is not correct, but that's because I didn't type in the message correctly. Now when the message is the same that I signed, the browser knows that it's me that sent the message. So if it's fault again, it sees that, and it knows that the message is tampered with. Another example, I will be using Firefox here. It's also using the polyfill because Firefox doesn't implement the API yet. So I generate a key. Copy it. Generate key. And now I will send a message. And here I will do it in the window where I put in the public key, because I want to encrypt the message with the public key of the other party, because I want the message to be only readable by the person to which I sent the message. So I will send devox is cool. Now when I copy the message, the encrypted message, you can see that it can decrypt the message. So, just to show you that in fact the keys are in the JSON key format, I will decode the key, and here you can see that it's just a JSON object where all the fields of the RSA key are encoded in. So what is the implementation status? IE11 and Polycrypt, they implement an old version of the spec, and they you might have noticed that in the examples that I was using an operation or calling the function to, for example, generate a key, and then use a method den, and then on that I provide the callback. That's in fact using promises, which is a new API, a new DOM API that is currently being spec'd out by the working group responsible for the DOM spec, and you will see a lot of other W3C specifications starting to get used using that new API. But we quite lately switched from DOM events to the promises, DOM promises. So that's why IE11 still has the old DOM events implementation, because they had their developer preview before we switched to the new version. So if you want to use it now, it's a bit tedious because you have to write your code using or detecting if it's still using the DOM events old way or the new way, how Chrome implements it using promises. But yeah, of course it's doable because yeah, it's only a couple of lines to make the switch. I did it in my examples, but in our next release, IE will switch to the promises version of the API. Yeah, Chrome implements the latest version, but as I've said during the demo, they currently don't, or they support import key and export key, but not with JSON keys, but only raw keys, and you can only you can't import the asymmetric keys using the raw format. Firefox and Safari have no public implementation yet, so that's why I used a polyfill in the example for in the demo. So what's next? So we're actually tomorrow and Friday we're having a meeting with a web crypto working group in China to work out the last problems in the spec, so we can go to last call. I of course won't be there because I'm talking here, but all the other people are in China now. After that we go to last call, we ask for, or that's a W3C process, we ask implementers for feedback, but also other people that want to use the API for feedback. So you're really welcome to send your feedback to our mailing list about improvements or suggestions. After that, we will start writing test cases, and if that's all done, then we can go to candidate recommendation and become a W3C recommendation. In the current version of the API, we didn't implement, or in a previous version we implemented the streaming API so that you can, for the encryption, keep on providing data So you can create or start your encryption, provide some data, then process more data, and when you're done, you could call the finish method to do the actual or get the result. But we decided to withdraw that streaming functionality because there is also another working group, or in the HTML5 people decided that there will come a new streaming API, the Streams API, that probably is going to be backwards compatible, but they're not sure yet. So we decided to wait until that API got fleshed out, so that we can use that API to support streaming. Another thing that that's more the company where I work for are really interested in, and there are some other people. We want to be able to access smart cards or other secure elements to sign or encrypt documents, especially in Belgium, where you have a Belgian electronic ID, which is a smart card. It would be nice that you can sign your tax letter using a standard using the standard JavaScript API, and not needing to use the Java applet as it is today. And there are of course, other use cases for secure elements, like identifying people in a company and things like that. Are there any questions about this? Yes?
What's the status on access to smart cards and those types of operations?
So there has been done some prototyping, but there are the browser vendors aren't willing to implement it. So it's still it's something that we decided in the working group. That's not something that we're going to do in the first version of the API. It might be something that we're going to do in a later version of the API, but if people want it, it's really good that you make it or send questions about it to the mailing list or or make it public that you want it, because the problem is that in the US, smart cards aren't used that much, and the browser vendors work or are from the US, and that's why it's not that important for them. But if people want it, then it's probably going in the next version or a future version. Other questions? Yes?
Is there any plans to improve user feedback?
Sorry, can you speak a bit louder?
Is there any plans to improve the user feedback? For example, is there any visible sign that I'm signing something and generating a key? If I upload a file, how can I be sure that it's encrypted and not sent to the background?
Yeah, that's a good question. So the question was, is there any visual feedback from the browser that you are actually signing a document or encrypting it, and when your key is used and for what it's used? So for now, it isn't, because the only way to get access to a key is using JavaScript, and all the keys that you generate are bound to the domain. It's the same origin policy like all the other security on the web. So if it's only the site that generated the key that has access to the key, you can of course export it and provide it to somebody else, but then it's your it's the app's responsibility, and you can of course use other methods to communicate, like post message. But because now it's a JavaScript, and you're in fact only the JavaScript can do it, and you're trusting the application that is doing it. So Sorry.
If I want to store a file encrypted on a server or service, but then I have to load the JavaScript from the same service, right?
Yes.
So they could tamper with the JavaScript and just, at that point in time, send an unencrypted also?
Yeah, that's a two-fold answer. So yes, they can do that, but that's with any other native application. They can you have the same problem. With JavaScript, you might be even a bit more confident because you could read the JavaScript. Of course, that's not always the case because they can serve a different JavaScript. But yeah, no, there is currently no solution for that. But yeah, it's not solved in any or that I'm aware of in any other case either. So yes.
Sorry, but one of the things you're saying is that the purpose of this crypto is to guard the information that we exchange with the service because we don't trust that. But if we don't trust that, how can we trust the JavaScript that's serving up to use that?
No, it's a difference because of not trusting the server. If you're using an application, I think that you have trust that the application does what it claims that it does, but you don't want your document to be there on their servers decrypted, because then they can or if there is a security breach, they can touch the document, and if they encrypt it using their keys material that is on there, then that key material also has to be somewhere there. So if there is a breach, maybe they also get that access to that. If it's done on the client, only the key is on the client side, and then they have to if only accessing the data on the server won't give, or if there is a breach on the server, you won't be able to get access to the private key there.
For example, with signing in the browser, you showed the signing the signatures and the green comes up.
Yeah.
I've got no idea what the JavaScript is and whether it's lying to me about it being okay.
Yeah, but that's the same in any other.
Well, no, because the JavaScript's coming over the same channel at roughly the same time as this material, whereas in other applications, non-browser based, you've got totally different channels.
Yeah, but if you're using TLS, that's why I said that you have to use TLS. Then it's an encrypted communication, so you know that it's from the other server if the key is not hacked or something.
But that would also guard your data, wouldn't it?
Sorry?
Doesn't that also guard your data?
Yes, at that point, yeah.
Okay.
But only at that point you're. Yes. So that depends on the. Oh, yeah, the light is quite bright. Sorry. That depends on the implementations. We let it really vague in a specification, so it's the browser or the implementer of the spec that decides that. So, in fact, it will be for sure somewhere where another web application can't access it. So it will be on the file system. If it's encrypted by or secured by a secure element that we don't mandate. If it's a good browser, then probably it will be stored somewhere with a secure element, so that only the browser can access it, and you can't go behind the back of the browser and if you get physical access to the system to get the key. But that depends on the implementation. Are there other questions? Yes.
Is there support for embedded keys?
You mean keys that are on the machine but not generated by the web application? Yes and no. There is the key discovery API that allows you to get access to pre-provisioned keys by name, but until it's how it looks today is that major browsers are not going to implement that part of that spec for applications on the web. There are indications that they might do it for example, for most browsers, or a lot of the browsers now also have their OS version. For that, you will be able to access keys in the system store, but for now not, and that's something that might change in a future version, but in the first version, sadly, the answer is no. Are there other questions? Oh, yes?
Is there going to be support for the TLS origin grid certificates? OBC?
So you want to get access to the TLS layer. In version 1, no, it was originally in the charter that that there will be access to TLS, but there were some in the it not made it to the first specification there. Yeah, in a future version probably also. So yeah, as it turns, or the questions show you there, yeah, it's only the first version of the API that we wanted to get out really fast and get implemented by all the browsers, because if it's easier if you only have to please one or two browsers, but then you can't use the API on the web because you don't know, you want to be able to use it everywhere, and that's why we had to make some compromises and defer certain parts to a next version of the specification. Are there other questions? Okay. So here are some references. So the slides are available online. The demo that I showed you, all the source code is available at GitHub. You can have a look at it and play with it. So this is the place where the specification is available. There will be a new version soon. So that was it. Thank you.